Greetings! In this video, I'd like to take another look at solar flares, but this time on the effect the solar flares have on the ionosphere and how that changing ionosphere affects the reception for the SID monitors and signal that we pick up with our antennas. The ionosphere is a layer that begins somewhere around 60 kilometers above the Earth's surface. It has a lot to do with the electron density and the varying electron density as you go up in altitude above the Earth's surface. Like most people have heard of the atmospheres above the Earth, the troposphere, the stratosphere, and so forth, and where you fly and how high you are. But the ionosphere is something that's very different. The ionosphere occurs because the radiation from the sun, the UV in particular, is a lot of energy, and they react with the molecules that are in the atmosphere, the oxygen, the nitrogen, and the nitrogen oxide. And that energy basically dissociates electrons, so that you get all these free electrons flying around, and all these charged particles floating around, and that creates kind of like a layer of where radiation has a little bit more difficulty going through it if it's too thick with electrons. Um, so the different regions that are basically formed during the day due to the sun's um, UV radiation on the atoms in the atmosphere creates these different layers, and they're approximate. So, somewhere around 100 kilometers is the E region, the F region. They split it into two. Um, Primarily with the SID monitors, we're concerned with what's going on in the D region down below. At night, the sun's gone, but there's still a little bit of ionospheric response because there's cosmic rays from all around the universe are still bombarding the Earth, and those basically are ionize the atmosphere in the same kind of way. And what basically happens in this D layer, if the density of electrons is high enough, it'll actually allow the AM waves, or I'm sorry, the shortwave radio to bounce and be received far, far away from the source. So basically, direct transmission for this person here would not be possible because if the waves just went straight out, they'd get kind of weak by the time they try to bend around. But by bouncing off the ionosphere, that response can be received by a person, halfway around the globe. Um, so it's really pretty simple. And then when we're looking at our antenna, we primarily are pointed towards Cutler, Maine, Naval Transmitter NAA, which sends out a signal at about 24 kilohertz. We're making an attempt to try to pick up some of the other antennas by kind of adding an extra antenna in a different direction and possibly finagling the direction to try to maybe pick up Pearl Harbor a little better since Maine is kind of closer. Here's a look at the flagship of the naval transmitters up in Cutler, Maine. It's been around since the 60s, and it's pretty powerful. It's one of the more powerful ones in the region. So it's a whole group of different transmitters in order to communicate with submarines all around, far, far away. So in order to communicate with a submarine, you need to have a signal that bounces off the ionosphere, will bounce off the Earth and the ocean back up to the ionosphere and eventually be received by a sub many, many miles away. So going back to flares, they come in all sizes. You've got big ones and you've got medium ones. So like this is a big one here on the left. It's an X2, and this is a pretty good. I can't say it's medium, it's moderate. This is like a 9.8. But there's different size flares. And how do we measure those flares? Well, the flares are measured by a satellite in geosynchronous orbit. NOAA has several GOES satellites. They have several instruments that are used to measure cloud layer, but we're primarily concerned with the X-ray instrument that are on there. There's two different wavelength ranges. There's the hard X-rays, which are short, zero point 0.4 to 4 angstroms, and the softer X-rays, which are longer wavelength, 1 to 8. But we use the GOES satellite to look at the X-ray signature of a flare. That flare takes about 8 minutes to go from the sun to the Earth. Um, so it's a pretty quick response, and the flares have a classification. ABC, and I guess instead of going to D, they decided to go moderate because really more worried about the moderate and the strong, the X flares, in terms of the effects they have on radio communication and satellites. If an X flare is measured by a satellite, that means there's some junk coming, a lot of ions and a lot of particles coming, and that could do some damage to electronics and satellites. So that's why they have like blackouts that occur. It's a logarithmic scale, so a C is, if C1 would be 10 times stronger than a B1, and M1 would be 10 times stronger than a C1, and 100 times stronger than a B1. And X flare, X1 would be 10 times stronger than an M1, 100 times stronger than a C1, 1,000 times stronger than a B1. So we're primarily concerned with flares that are upper C's, C8, C6. Those are picked up pretty well with the SID monitors. The M's definitely, and the X's are like, wow, those are the whoppers that we look for. And luckily, there's not a whole lot of X flares because that would wreak havoc. But this is like looking at the sunspot cycle from 1988 to 2016. So here's where we have solar maximum, sunspot maximum, and you can see there's X-ray flares here. There's none during a minimum in between here. You do see like there looks like there's one that popped in here almost. Nope. But there's not a whole lot of X flares when there's not a whole lot of sunspots. So the number of sunspots is somewhat proportional to the strong flares. And you can see there's a lot of C's and M's in between. If we look at all of them within an 8-year period, most of them are going to be C's and M's. Um, and not as many are going to be your X's. They're not going to be that clear. So in the last solar cycle 24, these are your basic numbers. And if you remember a picture from one of the videos, solar cycle 24 wasn't a really big one. Um, Number 25 is looking to be bigger than 24. So it won't be double as many, but it might be in 60 or 70 X flares to worry about. And we're just approaching maximum in the next year here in December of 23. Um, and again, as I mentioned before, the sunspot cycle kind of follows along with those flares. So here's the solar cycle 24. Um, So the length of the flares are somewhat significant. It's from minutes to hours. So over here on the right is like a 20-minute flare. It's not too bad, not too shabby. Maybe even this one over here that looks like it's almost like a B class flare. It looks like it's about 20 minutes or so. You've got your soft X-rays, which are your, 6 angstroms or so. The hard X-rays, which are very short, and you have radio bursts also. And here's the M 9.8 class flare from November 28th, I believe. Um, and you can see that it's almost 2 hours long in terms of an event. So some of these can be significant. It looks like there's a little baby one in here too that might be a 20-minute flare. Again, they occur at sunspots. You have the two sunspots, a north and a south pole, creating a coronal loop. And there's different things that happen with that loop, or prominence, I should say, um, as the magnetic fields are kind of interacting. Um, the chance of coronal mass ejections is huge with an X class flare. With C class flares, you still have a little bit of stuff that comes along with them. So there's still some concern, but not as much. Um, the M class flares do have stuff that comes with them. And there's little radio blackouts that you can have depending on your location. But with the X's, you always get material that's going to be coming towards the Earth, and you need to be very careful with electronics and radio communication. This is looking at the triggering mechanism for many of the CMEs. Sometimes the flares, I mean, sorry, the loops just start to form and they just quickly just blow off. But in most cases, this is kind of what happens. So you can see in this picture, you got some prominences and so forth. But what you look for is that magnetic field lines will kind of connect, disconnect, and some of the material goes up, some of the material goes back down. So this is a nice video that'll show this. If you look in the middle, how here's their connection, and those two magnetic fields are going to separate. And this is an actual video. You can see here they're starting to make like an X, and they're starting to separate. The two fields have disconnected in this case. Material is now going to be blown off, and you get X-rays, you get ultraviolet, you get microwaves, you also get radio bursts. So the radio Jove here at the Cincinnati Astronomical Society will pick up those radio bursts in the FM region because it's basically looking at 20 megahertz. There's multiple wavelengths that are sent out in these interactions and these flare events. Looking at the ionosphere. So again, the ionosphere is starts about 60 kilometers above the Earth. Um, the ionization is directly related to how much UV comes in, radiation from the sun, essentially. And during the day, you have different layers that are formed, and they're based upon electron density. And this is kind of a chart looking at those values. So the distances will vary. Those aren't direct, and it's kind of hard to see the difference in the layers sometimes. But you can usually tell by what frequencies are bounced. So there's a relationship between um, the frequency and the frequency that can go through uh, the ionosphere and how dense that ionosphere is. The more dense the ionosphere is, the lower the frequency that will be able to escape. So with the D region, it's not there at night. It's there's your electron density, like 1.5 times 10 to the fourth, and or 15,000 electrons per cubic centimeter. And as you go up into the F layer, now you're talking in millions, a million electrons per 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 cubic centimeter. Because you can see, like at noon, there's like a million in the F layer, and at midnight, when the sun's not out, there's 100,000. So that's a factor of 10. So it's a significant difference, and that has everything to do with how radio waves can be reflected. And not only is the ionosphere different um, night and day, but it's different with the different cycles. Because in solar maximum, you have more flares. The ionosphere is going to be responding more. Solar minimum, there's less flares. Um, and it plays a critical role in how waves are reflected, how we communicate, especially with things at long distances. You need that ionospheric response um, to be able to communicate at long distances. If the ionosphere gets all just uh, messed up from a flare event, there could be radio blackouts, there could be communication loss. And everything has to do with like I mentioned earlier, the electron density. The electron density and frequency are related to each other. Okay, I'm going to pretend it's a normal day. So the low frequency waves, like from the NAA transmitter, are reflected off the ionosphere, and you'd like to communicate with the GPS satellite in low Earth orbit to check out your position, or you're a ham operator up in the FM range, and you're relying on site to site for view. I'm sorry, not FM, but GMRS radio or some other radio that doesn't travel too much distance. So there's a flare event, and that causes the ionosphere to get um, more energetic. There's a higher electron density. So now, rather than that wave going out, reaching the satellite, it instead never reaches the satellite. It bounces off the ionosphere. So you can't get and communicate with that GPS satellite, um, which would not be good. And if you're using the high frequency band for communication, those radio waves could be completely absorbed, so you get like a blackout. So it can be very dangerous, especially myself. I'm an off-roader, so I rely on that communication sometimes with repeaters to make sure if something happens, I got a way to let somebody know I'm in trouble. Again, this is showing how if you're under normal conditions, you can pick up the satellite, but if you have a lot of X-rays, uh, extreme ultraviolet, that's going to cause the ionosphere to respond, and that communication will be blocked. There'll be disruptions in the GPS and total blackouts in the high frequency regions. Um, and when we look at the ionosphere effects with the SID antenna, it basically allows us to look at that D layer. Um, that D layer is formed during the day, and it's the strength of the signal depends on the interaction with that D layer. If it reflects nicely off the D layer, we get a very strong signal. If it ends up the D layer's not as electron dense, some of the radio waves will be absorbed instead. Or there are very low frequency transmitters around the world, and our SID system could theoretically pick up any of the electromagnetic waves from these transmitters if our antenna is big enough and pointed in the right direction. So it's not against the law to pick up the electromagnetic wave, the carrier wave, but it is against the law to try to separate the wave and listen to what they're talking about. And that's exactly the SID monitor. So there's a picture of the antenna. We're going to look at some data um, from a researcher in Ireland as a comparison. So here's the kind of data from Ireland to Cutler, Maine, rather than ours. A nice quiet day. There's that little lump where here's high noon. We have a sunrise effect and a sunset effect because the ionosphere is transitioning back and forth. And at night, um, the signal is strong because it's just bouncing off. There's nothing there. There's no a lot of ions. Everything's just bouncing off the F layer. So the response is really pretty good. And you might have noticed this, old people like me remember listening to AM radio. It was much better in the evenings. You could pick up Chicago easily from Cincinnati, Kansas City, New York during the evenings because of that effect. During the day, there's a lot more ionospheric disturbances, and those waves are getting absorbed. During a flare day, um, the ionosphere kind of responds, and the D layer gets more reflective. So the signals are going to be stronger. And it varies with the way the flare. So it's an amazing way to measure X-rays indirectly. The GO satellite down below is measuring an X-ray flare in the X-ray band. This would be the zero point 0.5 to 4 angstroms, and the red would be 1 to 8 angstroms. And we could measure, or I could say the person here in Ireland was measuring the ionospheric response to that X-ray flare event. And you can see that they have very similar shapes. So if you look at the GO satellite, there's that C event. See the kind of tail that it has. The M is a little bit bigger. It has that long tail. This one, very similar. The C event here is really long for some reason. I don't know why, but it's just that's the way it happened. These are like magnitudes. Um, so I hope this was helpful in understanding a little bit about solar flares, how the solar flares affect the ionosphere, and how the ionosphere responds to those solar flares affect the strength of the signal that we pick up with our super SID monitor. Uh, Thanks and have a great day.